Marvin.
Hello everyone. Now we discuss about the Hall effect, what is the Hall effect and how we find the coefficient of Hall effect. Firstly we define the what is the Hall effect. Hall effect, that means according to Hall, when any semiconductor which is placed in external magnetic field, the current induced in the semiconductor is direction of the current directly perpendicular to the magnetic field, external magnetic field, and by which the electric field which is produced in the rod or the semiconductor in direction perpendicular to the both direction of magnetic field and direction of electric field. How it is? We show by the diagram. In this diagram, that is the external magnetic field and it is the external semiconductor which is placed in magnetic field. That means the direction of the current in which the semiconductor in x direction and the magnetic field is in direction of y direction. That means the current and the direction of magnetic field, external magnetic field, it is perpendicular to each other. And when we place the external semiconductor in magnetic field, external magnetic field, then the produce of electric field in semiconductor in direction of z. That means the electric field which is produced, which is developed in the rod in direction of the both the direction perpendicular x and y. That means the electric field is directly proportional to the both the direction x and y. That means the direction of the current is x direction and the direction of the magnetic field y direction, and the which is field electric field produced in the rod, the direction in z direction. The three are direction, they are perpendicular to each other. If suppose they are the n type of semiconductor, external semiconductor we have, then that means the charge carriers in the semiconductor is electron. That means I have the semiconductor rectangular cross section area, the semiconductor. Suppose there are electrons in semiconductor. It is shown by the E. The electrons in the semiconductor, when we apply the external electric field, then the current flow, that means the electrons are flow in x direction with the velocity, it is the drift velocity Vx, and flow in x direction and oppose the direction of electric field. Okay. And now we place this external semiconductor in external magnetic field as Z. It is shown there. Now we place when in external magnetic field, then they experience the Lorentz force, and the electrons which is experience the Lorentz force, it trip in negative side. The charge experience the Lorentz force, the electrons, the force is downward, the electrons, then the negative charge accumulated on the lower surface and the positive charge accumulated on the upper surface. Now if the semiconductor, now we firstly talking about the n type of semiconductor. Now we have the p type of semiconductor, that means the charge carriers in semiconductor are holes. So the rectangular shape of the semiconductor, external semiconductor of p type, the holes in the semiconductor, when we apply the external electric field in direction opposite to the direction of current flow, then the holes strip with some velocity, with the drift velocity Vx, and when we place the semiconductor in external magnetic field as Z, that when we place the in external magnetic field, they also experience of Lorentz force which is downward and the positive charge accumulated on lower surface and the negative charge accumulated on upper surface, and there the field contained electric field which is that, and the electric field in which the reversible is shown by the EH. Now if taking the condition of n type of external semiconductor, that means this condition, the force on electron due to the Hall field is E small e capital E Z, where E is the electron and EHF is the electric field which is produced in the semiconductor, and the Lorentz force on electron due to the magnetic field, that is equal to EVx as Z, where E is the electron, Vx is the drift velocity by which electrons drift, and as Z is the external magnetic field, it is work in negative y direction. In steady state, the force on electron due to the Hall field is equal to the Lorentz force on electron due to the magnetic field. That means EH is equal to EEx as Z. Now we find the value of find the value of electric field EH is equal to Vx as Z. Then the Hall voltage Vx is equal to EH into B, where B is the width of the rod. That means now the value of the Hall voltage Vh is equal to Vx as Z B. Now putting the value of Vx as Z here. According to Hall effect, when any semiconductor which is placed in external magnetic field, the current produced in the rod in direction perpendicular to direction of the magnetic field, and the electric field which is produced in the rod in direction perpendicular to both the direction of the current and direction of the magnetic field. The electric field which is produced, which is known as the Hall field, and the voltage developed across the end of the rod, which is known as the Hall voltage, is shown by the Vh. The Vh is the Hall voltage. The value of the Hall voltage is equal to Vh is equal to Vx, electron dip velocity of electron as Z, the external magnetic field. B is the width of the rod, which is used in semiconductor. Now we find the Hall coefficient. We know that the density of the current density is shown by the Jx is equal to n, the number of the electrons, minus p, the electrons, and Vx, the drift velocity. Now find the drift velocity. Vx is equal to minus Jx upon n. Then the electric field, Hall field, EH is equal to Vx as Z. We know that. Then putting the value of the Vx is equal to minus Jx upon n, where Vx minus 1 upon n Jx as Z, where minus and 1 upon n is the proportionality constant that is shown by the EH directly proportional to Vx as Z, or EH is equal to R Hall Jx as Z. That means where H or R Hall is equal to minus 1 upon n E. There R Hall is the Hall coefficient, the value of minus 1 upon n, the unit of centimeter cube per coulomb, where the negative sign is show that the charge carrier in the semiconductor, external semiconductor, is electrons. If there is a positive, that means the charge carrier in the external semiconductor is positive. That means the semiconductor is n type of semiconductor. If there is the value is positive, that means the charge carriers are Hall and the semiconductor is p type. If P is the width, T is the thickness of the rod, I is current flow in the rod, then the current density Jx is equal to I upon dV. Then from equation of this, EH is equal to minus 1 upon n Jx as Z, we know that. And now we putting the value of current density Jx, I upon Vd here, then the minus 1 upon n as it is I Vd as Z. And we know that the value of the Hall voltage Vh is equal to EH into B. Then Vh is equal to, now putting the value of Hall field, minus 1 upon n I upon Vd, V as Z. There B and B are the cancel. Then Vh is equal to, we know that this value is equal to the Hall coefficient. I mentioned R Hall and I as Z upon V as it is. Now we find the value of the Hall coefficient is VH, D is the thickness of the rod, and I as Z. That is the value of the Hall coefficient. By which we find what is the value of Hall coefficient. This is the formula. Now we perform the. Welcome again. Previous section we discussed about the theory of Hall effect, and now we perform the practical how we find the value of Hall coefficient. This is the completely Hall effect setup. That is the digital Gauss meter, and it is connected by the rod. It is the probe. It is made by the indium arsenide. This is two pole of electromagnet. That is the constant current power supply. It is connected by the Hall probe. That is the semiconductor, by which we find the value of this semiconductor Hall coefficient, and it is made by the germanium, and it is the extrinsic semiconductor P type. The thickness of this 0.5 mm, and this is the power supply for electromagnet. It is set at 1 ampere and connected to the electromagnetic pole. Firstly you find the value of the magnetic field by this probe. It is putting the in external magnetic field, and note the reading by the digital Gauss meter. It is approximately 1000 Gauss. Okay, mention here the value of the external magnetic field, 1000 Gauss, and 1000 into 10 to the power minus 4 Tesla. This is the thickness of this crystal, and it is in 0.5 into 10 to the power minus 3 meter. The least count of ammeter is universal 0.01 milliampere. The least count of voltmeter 0.1 millivoltmeter, and least count of Gauss meter is 1 Gauss. It is the digital meter. This is the provide the supply by this electromagnet to the pole and switch on the constant current supply. Now we putting this Hall probe in between the electromagnetic pole and find the reading of input current and output Hall voltage. By this knob we increase the current, then corresponding find the voltage value of this voltage. That is to show the Hall voltage. Now again increase current and note down the reading of Hall voltage. This process continuously increases current and continuously note the reading of Hall voltage. After find the reading, put up in the table input current, Hall voltage, and also find the Hall field EH by the formula. Now they calculate the Hall coefficient. We know that the formula of Hall coefficient is VHD upon IZ, where V is the Hall voltage, D is thickness. We know that the thickness of crystal 0.5 mm, I is the input current, and SZ is the magnetic field, which is find that. We also mention here Hall coefficient is equal to tan theta D upon SZ, where tan theta is the ratio of slope of the voltage, Hall voltage and current, and also it is change in voltage and change in current. For this we plotted the graph between the voltage, it is the Hall voltage, and current is the input current I and VH. When we plotted the graph, we find the straight line, and after find the straight line, we find the change in Hall voltage and change in current. That is show that the change in voltage and change in current, del VH upon del I. That is, by this we find the value of tan theta. After finding the value of tan theta, this is put up the value in this equation, and we find the value of Hall coefficient. So by this experiment we find the value of Hall coefficient. This is experiment, it is the Hall experiment, and it is effective for finding the charge carrier in which the semiconductor, and what is the semiconductor we use, which is type of semiconductor we use, N type or P type, the mobility of charge carrier, and the number of electrons per unit volume placed in semiconductor. So this is the total experiment of Hall effect, and now we discuss about. Thanks for my supporting staff.